the definition of capacitor, capacitance, dielectrics, what an electric is used for, and sort of a sketch of what a capacitor looks like on the board, the plate. So you have two parallel plates, one positive, one negative, positive charge, negative charge, overall charge Q. Each plate has an area, and there is a distance between the plates. That's how you find the capacitance, C. That's how you find the electric field inside a parallel plate capacitor, where this sigma is the surface charge density. And the relationship between voltage, electric field, and the distance between the plates. Very important is what we use also last class, that the electric reduces the field and the voltage, but increases the capacitance. Lowercase k is the dielectric constant. Okay? No units for this. It's just a value that depends on the material that you use. The electric can be different materials, insulating materials. So that's what gives you the value of K. Normally, if you're working with a capacitor without the electric, we say or we write that it's an air-filled capacitor. An air-filled capacitor is a capacitor that doesn't have a dielectric. All right, or we assume that the dielectric is 1. So any dielectric or any value of 1 for K means that it's an air-filled capacitor or an empty capacitor. Nothing between the plates. Okay, so let's take a look how we use some of these equations. Here, you have a capacitor with parallel plates with area 0.04 meters squared and a distance between the plates of 4 centimeters. They ask you to find the capacitance. To find the capacitance of a parallel plate capacitor, we can use in this problem this equation, right? Where E naught, the electric permittivity of free space, is this value. All right? So we have the area, we have the distance. We just have to be careful with the units. So this is E naught. The area is already in meters squared. So you have to write the area in meters squared divided by the distance, 4 centimeters, 0.04. Well, value-wise, they are the same. So the capacitance is 8.85 times 10 to the negative 12, or you can write 8.85 picofarads. Or, yeah, pico is 10 to the negative 12. All right? So as an example there, the other example will be a parallel plate capacitor like that, where they give you the voltage between the plates, 25 volts, positive, negative, a distance of 2 millimeters between the plates, and an area of 6 centimeters squared. So now you have to be careful with the units. That's the area, that's the distance, that's the voltage. What is the electric field, right? What is the value of the electric field? Start with that. So the electric field, you can use this equation, or here, the electric field is the voltage divided by the distance between the plates. So the electric field will be the distance, the voltage, divided by the distance. Now, that distance is 2 millimeters. 2 millimeters is 2 times 10 to a negative 3. So 25 divided by 2 is 12.5. Multiply, or what? 12.5 times 10 to a positive, times 10 to a 3. All right? Which 1, 2, 3, 12,500 volts per meter. Okay? So that's how you find the electric field using this equation. All right? Now we have to find the capacitance. Just like this, I have the area, I have the distance. So we just have to find the capacitance. So the capacitance is E naught that's E naught, parenthesis, area. Okay, so the area is 6 centimeters squared. If you want to change that to meter square, you're going to do this. 1 meter is 100 centimeters, but you have to do this twice. So it will be 6 multiplied by 10 to a negative 4 meters squared. So that's what you do. So here you write 6 times 10 to a negative 4. And the distance, just like we used before, 2 times 10 to a negative 3. So 6 divided by 2 is 3. Then we have to multiply that by 8.85. That's 26.55. 6 divided by 2, that's 26.55 multiplied by 10 to a negative 4 divided by 10 to a negative 3 is 10 to a negative 1 times 10 to a negative 12 is 10 to a negative 13 farad. Now, if you want to use the prefix that we used before, we multiply this by 10 and divide this by 10. So it's about 2.66 times 10 to a negative 12, which gives you 2.66 picofarads. Very small, as you should expect. Electric field, capacitance, and now we're gonna find the charge on each plate. So now you wanna find the value of the charge Q. So what's Q? So to find Q, we have to use the original equation for capacitance. For any capacitor, capacitance is charge divided by voltage. So I have the capacitance and the voltage is 25. Now, my capacitance, be careful with the units. The capacitance is 2.66 picofarad. That's equal to Q divided by 25. So if I do the math, I get this times that, 66.5 picofarads times 1 times volts will be picocoulomb. Not coulomb, not just coulomb, but picocoulomb, 10 to a negative 12 coulomb. So that is how you find the charge. This is the capacitance, and that was the electric field. Okay? So that's pretty much how you use these equations. Let's take a look at one problem with dielectric. All right. So you see how we use dielectrics as well. So there's one here in the textbook. So while I'm looking for this, when you are working with capacitors, capacitance, and dielectrics, if you have a dielectric, remember that the dielectric will change the value of the electric field into what we call the dielectric strength. Now let's see if I find this problem. Okay, why is it exactly? Air field, capacitors. Ah, there it is. So let's see. You have a parallel plate capacitor that has a dielectric. So example here. You have a parallel plate capacitor like that. And inside the capacitor, there is a dielectric like this. And this has a dielectric constant K equals to 3.1. And the dielectric strength, so this is what they tell you, that the dielectric strength, is equal to 1.5 times 10 to the 8, very large, volts per meter. Now, the one or the desired capacitance is of 0.40 microfarads. So they want that capacitance. And the voltage between the plates must be 5.00 kilovolts. So find the minimum area for that, or find the area of the plates. Okay, so quite some information here, right? That the electric constant is gonna increase the capacitance, but it's also gonna change the electric field, the E. This is the electric strength. The electric strength is the electric field inside the capacitor with the electric. So is the reduced field due to the electric. That's what this is. That's the capacitance that you want for the capacitor. And it should withstand 5 kilovolts. To find the area of the plates, you need this equation. So area, you have the capacitance. E naught, you know what E naught is. So you are missing the distance. But the distance between the plates, where can you find the distance between the plates? Well, you have the voltage and you have the electric strength. If you have the electric strength and you have the electric constant, you can find the E. And E equals to voltage over distance. There you are. If I have the distance and the area, I can find the capacitance. So that's what you do. Okay. That's what you do. So the electric strength is equal to the original electric field divided by K. That electric strength is 1.5 times 10 to the 8. That's E divided by 3. 3.1. If you do the math here, you get 4.5 times 10 to the 8 volts per meter for the magnitude of the electric field. And then I can use that with a voltage. So 5 kilovolts is equal to E times the distance. There you are. So your distance is going to be very small. (1.11) or 1.1 times 10 to the negative 5 meters. That's the distance between the plates. Distance field. Now, to find the area between the plates, capacitance, which is 0.40 microfarads, that's E naught area, I want the area, divided by the distance, divided by this. There you are. Okay? So it's just a math exercise at the end. Let's finish it here. So there is the area. So that times that divided by that. So the area is 0.40 times 10 to a negative 6 multiplied by 1.1 times 10 to the negative 5 divided by 8.85 times 10 to a negative 12. So negative 6 times negative 5, like you add the exponents, negative 11, negative 12, or 10. 0.40 times 1.1 divided by 8.85 multiplied by 10, 0.5 meter square. Yeah. There you are. Okay. That's how you do this problem. So you see the steps, right? Dielectric strength, now remember, that's what it is. The units for electric field now are this. The relationship between voltage, electric field, and distance, very important. And the equation for capacitance. Okay. This equation, you are only going to use it when they ask you about, when they give you charge or they ask you about the charge. If not, you can use the definition that we proved last class. Okay. So let's do one more so we can go into the circuits. We can start introducing circuits today. All right. Tomorrow's class, we're going to start with current. So today I'm going to start introducing circuits of capacitors. And tomorrow we do current and circuits, and we finish with that on Wednesday and Thursday. So I'll let you guys know tomorrow whether or when and how the second quiz will be. It's most likely going to be on Thursday, all chapter 16. All right, so electric potential energy, and capacitors. All right. Okay, so the other problem was actually here, right? Oh, here it is. Okay. So let's see how we use the other equation that we have in here. So they give you again a parallel plate, empty. So given an air filled capacitor. So you have like that. Where the distance is of 1 millimeter. So this distance here is of 1 millimeter. And it says that the voltage between the plates is of 3 volts. So the voltage is of 3 volts. Find the surface charge density. So find sigma. All right. If they're asking you for sigma, the only equation that has sigma is the equation for the alternate equation for field. Sigma, we know that. So I need to find the electric field. E naught is, I already know. That's easy. I have the voltage. I have 1 millimeter, the distance between the plates. I can find electric field. The electric field is the voltage divided by the distance. So that will be 3 volts divided by 1 millimeter, which is 3,000 volts per meter. That's the electric field between the plates. Then 3,000 is sigma over E naught, which is this. All right. 26.55 multiplied by 10 to the negative 9. And the units for sigma are coulomb per meter square. There you are. So that's how you use that other equation there to find sigma. All right. Any questions about this? All right. So assignment 3 has several problems about this section. So make sure you work on those. I saw that many of you have finished assignment 1. The quiz was graded. I did provided feedback in a few of those quizzes, so make sure you check the notes. And now we're going to go into the last section of this chapter, which is introducing capacitors in circuits. So at the end of the day, that is one of the objectives of this course, is that you learn how to apply some of these concepts in electronics. So a few of you did a lab today where you have to connect a circuit. Now we're going to start talking about circuits. Today, I want to continue tomorrow when we start introducing resistors, currents, and different type of circuits. So let's see. I think I already have everybody. Okay. All right. So how do we arrange capacitors in a circuit? So circuits, simple circuits, can be divided in two types of circuits. You may have them in series or you may have them in parallel. And then the idea is to see how you can combine capacitors in series or parallel, right? Very important, okay, very important section of this chapter. So let's do capacitors in series. All right. So the notation that we're going to use for capacitors, especially in circuits, is like this. This is how you draw a capacitor in a circuit. So that's 1, that's 2, and that's 3. And they can all be plugged to a power supply like this. So I'm going to call this C1, C2, C3, B. So in series, if you have capacitors, you only have to worry about the voltage, the capacitance of each, and the fact that in series, the charge on each capacitor is the same. So the total charge of the circuit, we call it Q. So the total charge is Q. So V1 plus V2 plus V3 is equal to the V supply. So what happens is that in series, each one of these capacitors has a voltage V1, V2, V3. They are different. By conservation of energy, if you add them all, you get a voltage in the circuit. So how do I combine capacitors in series? Well, V total is the total charge divided by C. I want to call this C equivalent. V1 will be charge, which is the same charge Q over C1. V2 is Q over C2. V3 is Q over C3. So clearly, you can draw on. And V equals to, oh yeah, right? So Q cancels. So 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So that's how you combine capacitors in series. All right. How about in parallel? So how about capacitors in parallel? For capacitors in parallel, the way you draw them is like this. One, two, three, And then you have the voltage there. So I call this C1, C2, C3, voltage. Now, for a parallel circuit, for any parallel circuit, the voltage is always constant. So this is a V, V, V. That's because of this, by the way. See this? The endpoints all are the same potential. The potential difference is the same. The charge now splits. In series, the voltage splits, the charge is constant. In parallel, the voltage is constant, the charge is divided among the frame. So what is charge? The total charge is equal to C equivalent times the voltage. That's V. So here you have C1, V1, C2, V2, C3, V3. But voy a hacer cuando that's all V's. So V, V, V. And yeah, C equivalent is C1 plus C2 plus C3. There you are. That's how you join capacitors in series. That's how you join them in parallel. All right. So now we have to do the examples of this. So the examples are going to be a series of circuits. Assignment 3 has all these circuits. All right. You're not going to just have parallel and series, by the way. You're going to have combinations. So I always suggest students to keep track of the steps. You see, there are different steps. At the beginning, it's not that difficult, but it can be challenging when you want to split charge and voltage. See what I mean here? Let's see. So parallel series. So now we're in circuits. All right. So let's start with a easy one. You may have a capacitor by itself there, and then it's very common in different circuits to have loops and branches. So that's what I'm doing here right now. You have two like that. like that. So that's a simple circuit. Let's give values here. So 4, 2 microfarads, 4 microfarads. So those are the capacitance values. 3. There you are. And the voltage here, let's say, is 12 volts. What can you be asked? Find the equivalent capacitance. B, find the total charge on the circuit. And C, find the charge on each capacitor. Those are the typical questions you may be asked in a problem like that. Okay? So as I said, you're going to have combination of parallel and series. So what's the first step? You want to simplify the circuit. Let's start with a parallel. So for the parallel 4 and 2, you can add, or you add these two. To combine them, you add them. 2 plus 4, 6 microfarads. And then 3 and 6 are in series, clearly, right? So you combine them in series using the equation of the sum of the inverses. So then for part A, 1 over C equivalent is equal to 1 over 3 plus 1 over 6. So in this section, when you guys do the assignments, or the assignment, be careful because the numbers I'm going to give you are nice and easy like that. But in the assignment, they might give you questions with decimals. So if you have the calculator, you can use decimals. Or like, you know, if it was 3.2, 6.3, just use a calculator, convert it into a decimal, and then remember that you have to flip it to find the equivalent. Because the numbers are easy there, I can easily find the common denominator. Between 3 and 6, the common denominator is 6. So I write 6 here. That's the common denominator. And here I multiply by 2, by 2. So this is 2. And if this is 6, you just write 1. So that's 1 over C equivalent. That's 3 over 6. 1 over C equivalent. If you flip it, you get 6 over 3. And let's not forget the units. That's the equivalent capacitance. For part B, we're going to find the total charge. Q, I told you, right? Now to find Q, what we use is equal to CV. That's because, remember, C equals to Q over V. So you multiply and then that's what it is. The total charge is the equivalent capacitance. Oh, I'll show you something with this. 2 microfarads times what's the voltage in the circuit? 12. 12 volts. 2 micros times 12 volts, 24 microcoulomb. All right. So part A and part B are quite easy. Just combine the capacitors and then use the equation to find Q. The next part is where you have to be careful. Normally for the next part, you can kind of go backwards because you want to find a charge on each of these capacitors. Okay, all of this. Now, 3 is in series with 6, and 6 is a parallel combination between 4 and 2. So, because 3 and 6 are in series, the charge on 3 is equal to the charge on 6. See, the charge here is the same as the charge here. So, Q on 3 equals to Q on 6. Equals to what? What is the charge on 3 and 6? Is the charge of the circuit. The charge of the entire circuit is the charge on 3 and 6. And what's the charge of the circuit? There, 24 microcoulombs. So for this, Q total, which is 24 microcoulombs. So that's Q3 and that's Q6. But I want the charge on 4 and the charge on 2. That's okay. Q on 6 is 24 microcoulombs. 2 and 4 are in parallel. In parallel, not the charge, but the voltage is constant. So let's find the voltage on 4 and the voltage on 2, which, by the way, is equal to the voltage on 6. Now, the voltage on 6 is the charge on 6 divided by 6 microfarads. That's 4 volts. So the voltage on 6 is 4 volts. That makes it is 4 volts, 4 volts. Perfect. So now the charge on 4 is equal to the capacitance 4 microfarads multiplied by the voltage for 16 microcoulombs. And then the charge on 2 is the capacitance 2 multiplied by 4 volts, 8 microcoulombs. How do you check this is correct? 16 plus 8 is 24 microcoulombs. That's how you verify that what you did is right. Q on 4, Q on 2, and Q on 6. That's how you do problems where you have circuits of capacitors. I will do a couple more at least. But are there any questions?
Yeah, Professor, I have a question.
Yeah.
So Q3 is equal to 24 and Q6 equal to 24. Which one is equal to 24?
Yeah, because they are in series. Yep. Make sense? Well, let's do a couple more. Because the
Oh,
idea
one
is,
question.
huh?
I'm sorry. For V, when you say C equals Q over V, is that the V over like the whole thing, or like
Yeah, in here will be the V, the overall V. Yes,
all right, thank you.
this is with Q total. Q total. So C equivalent. C equivalent. Q total over V. Yeah. All right. I'm gonna leave there for you guys to keep if you are still writing it. While you guys are doing that, let's draw another circuit here. This right. 4, 12, 6, 2. Have a different setup. I'm using that in purpose to clarify a couple of misconceptions. All right. Find the equivalent capacitance. Find the total charge on the circuit. Find the voltage on each. D, find the charge on each. Actually, C and D, you can do them together. You'll see what I mean when I get to that part. I guess the first misconception or the misconception in this problem is how you combine the capacitors. You see, 4 and 12 are in series. 6 and 2 are in series, but you can get confused with a parallel setup. Like you could make the mistake of combining these two. 4 and 6 in parallel, 12 and 2 in parallel. This line is parallel to this line, but the whole line is in parallel. So you need to find the capacitance here and here, and then you combine them in parallel. But what's the capacitance here? The capacitance here is the combination of these two. And the one here is the combination of these two. So that's the first, maybe only misconception. If you combine 4 and 6 and then 12 and 2, you will get everything wrong. And we don't want it. All right? So let's do part A and B. Gonna be similar to this. Now, 4 and 12 are in series. So 1 over C, so I'll put like that, is 1 over 4 plus 1 over 12 microfarads. The units at the end for C are going to be in microfarads. Again, the numbers are good, very friendly, right? Very nice. 12 and 4, you combine them in 12. That's the LCM. Multiply by 3, multiply by 3. This is 3 plus just 1 here. That's 1 over C. So C will be, you flip it, 12 divided by 3 plus 1, 4, 3 microfarad. And then I'm going to combine 6 and 2. 1 over C prime, 1 over 6 plus 1 over 2. Again, easy. The common denominator is 6. 1 plus 3 here. So this is 3. 1 over C prime. So if I flip it, 3 plus 1 is 4. 6 divided by 4, which is 3 half, which you can say 1.5 microfarads. All right. So that's almost part A. 3 and 1.5, they are in parallel now, right? This is combined into 3. This is combined to 1.5. These are in parallel. How do we combine them when they're in parallel? Easy. We just add them. C equivalent is 3 plus 1.5, 4.5 microfarad. That's my C equivalent. Part B. Find the total charge. The total charge in the circuit is C equivalent multiplied by the voltage supply, 9 volts. C equivalent is 4.5 times 9. 40.5, okay, microfarads, 9 volts, microcoulomb. So A and B quite easy, right? Okay. Now let's find the voltage on each capacitor and the charge on each capacitor. You know what? It's easier to find the both actually, the charge and the voltage. Let's analyze. You have 4, 12, 6, and 2. 4 and 12, you combine them in 3, and then 6 and 2 were combined into 1.5. Now, 4 and 12 are in series. 6 and 2 are in series. But 3 and 1.5 were in parallel. So automatically, you know what's the voltage here and here. For part C and D. The voltage on 3 is equal to the voltage in 1.5, which is equal to what? The voltage on the circuit. Is it in parallel? So it's 9 volts. And if I have the voltage on 3, I can find the charge on 3 and the charge on 1.5. The charge on 3 microfarads, I have the voltage, I have the capacitance. So Q equals to CV. The charge equals to the 3 microfarads times 9. That's 27 microcoulomb. And the charge on 1.5 is 1.5 times 9 13.5 microcoulomb. And why do I do that? Because the charge on 3 is the charge on 4 and 12 series. So the charge on 4 is equal to the charge on 3, which is how much? 27. So the charge on 12 is also equals to 27. Now, what about here? The charge on 6 is equal to the charge on 2 equals to the charge on 1.5, which is 13.5. So the charge on 6 is 13.5 microcoulomb, and the charge on 2 is 13.5 microcoulomb. So these are all the charges. And then I found the voltage here and here, but I don't have the voltage on each capacitor yet. If I have the charge and I have the capacitance, it's very easy to find the voltage. Use this equation. Right? The voltage on 4 is the charge on 4 divided by the capacitance 4. .7 volts. The voltage on 12 will be now 27 divided by 12. Pues point 2.3. Yeah. 2.3 plus 6.7 is 9 volts. So that's how you find voltage on 4, voltage on 12. All right. And you can do the same for 6 and 2 microfarads. All right. So any questions about this? Any questions? The trick is to keep it organized. All right. It's always the same equation, but you just have to pay attention what they are asking. All right. Again, in the assignment, you have at least assignment three circuits like this. Okay. After the capacitance problems, the ones that we did at the beginning of class, you have questions like that involve circuits. All right. Let's take a look and let's try to do another one. That's the one we did. There it is. All right. Okay. Right. Let's give some values here. All right, that's a different setup. You have 5, 1 in parallel, and then the other one in, well, outside. To find the equivalent capacitance, 5, 1 are in parallel, and they are combined in series with 12. All right? Clearly, right? Again, be careful with this. Because there's a, we call this a junction here. So you cannot combine these two yet. You have to look at these two. So 5 and 1 are combined into 6. They are in parallel. You add them. And then 6 and 12 in series. So 1 over C equivalent is 1 over 6 plus 1 over 12. Like that. Right? So C equivalent, 12 divided by 3. That's the equivalent capacitance. The charge C times the voltage, 10 volts, 40 microcoulomb. To find the charge on each, well, I'm pretty sure everybody by now should know what's the charge on 12. What's the charge on 12 microcoulombs?
10.
Huh?
10.
No, that's the voltage. I'm looking at the charge. What's the charge on 12? It's by itself there. It's not being combined with any other capacitor. So what would be the charge?
40.
Yes. So it's 40 microcoulombs. It's in series. Which is also a charge on 6. So we found the charge on 6, the charge on 12. The charge on 6 is also 40. And then I can use that to split it. So the charge on 6 is the same as the charge on 12, which is 40 microcoulombs. Now the charge on 6, right, is equal to the capacitance on, it's equal to 6 multiplied by the voltage on 6. So the voltage on 6 is the charge on 6 divided by 6. That's 6.7 volts. Why do I need a voltage on 6? Because the voltage on 6 is the same as the voltage on 1 as the voltage on 5. So for example, the charge on 5 now is 5 microfarad times the voltage on 5, which is 33. Wait, what? Ah, yeah, 33.5 microcoulombs. Now, the total charge is 40. The charge on 5 is 33.5. That means that the charge on 1 is 40 minus 33.5, 6.5 microcoulomb. And that's how you split charges and voltages. Tomorrow, if you have questions about, topics for of this chapter or assignments, I'll be, well, you're gonna be in the lab anyway, so I'll be here at 10 a.m. All right, setting up the lab. So you're welcome to show up a bit early if you have questions, or after the lab. The lab is actually short. We can discuss any topics before class. All right. We're almost at the end of the chapter. I do want to start current fresh tomorrow. So what I'm gonna do to finish before we finish the class, I wanna do energy. All right. I kind of forgot that's also an important part on capacitors still. All right. The reason why we use them in circuits and in general, the reason we use capacitors is because they can store energy. So how do we find the energy in a capacitor? We have an equation for it. If you have a capacitor, like this, all right? You know there's an electric field. And now you know there is a potential difference or a voltage between the plates. Negative Q, positive Q, distance D, area A between the plates, so all that we've been discussing. And you remember that the energy, electric potential energy, is like that. Now, sometimes, or not sometimes, analytically, analytically, we actually use that. These are differentials, yes. And we know from what we did before, right? V is equal to Q divided by C. So if I do this, I get that the energy in a capacitor is equal to the square power of Q divided by 2C. That's the way you prove it. So that's the equation for the energy of a capacitor. If I use the relationship, right, this or what? I use this. Then I can use this as all right. So that's the equation for the energy of a capacitor. And you can actually find a nice relationship that we're going to use later. For now, see the equation there? The energy can always be found, in physics especially, as a factor of energy densities, like how much energy per meter cube, right? We do that in radiation physics, in astronomy, we use it a lot. In electricity and magnetism as well, of course. So how do we find that for this? I just have to use the equation for C. The equation for C, remember, is E naught area over distance. 1/2 C, and the voltage, remember, voltage is ED. So I can use that in here. What I will get here is 1/2 E naught area distance E squared. So for the first time, we get an equation that multiplies the area times the distance. The area of the plate times the distance. Remember, this is a three-dimensional figure. A capacitor is a three-dimensional object. On the board, I just projected. So area times distance, the area times distance, is a volume. There you are. 1/2 E naught E squared times the volume of the capacitor. That's the energy. So if I divide energy over volume, I get what we call mu E, which is 1/2 E naught E squared. This is what we know as the electric energy density. There is a similar factor for magnetic fields. When we get to that point, we will combine them to show you, well, when we start talking about radiation, that will make more sense. Let's do a problem to show you how to use some of these equations, all right? I'm gonna leave that in there so you can write it down while I take a look at this and see what good problem there is. Oh, there it is. One like that. Okay. Imagine you have a capacitor connected to a 70 volts battery. So it's quite a lot. And the capacitor has a capacitance of 4 microfarads. How much energy is stored? is that's the thing about capacitors. The capacitor, the idea is to store energy that you can use later. For example, as I mentioned last week, the defibrillator that we use to resurrect the heart of a person, right? To reignite the heart, uses capacitors, right? You can charge the defibrillator and then you can place it on a person's chest to reignite the heart by passing the charge, right? You basically send an electric current to reactivate the person, you know, to resurrect the person. Anyway, when they give a question like that, you just have to think, right? What are you being given? You are given the capacitance, and you're given the voltage. You don't need a charge because you can use this 1/2 series code. So the equation for energy, remember guys, the same U, but this is only for capacitors. I'm gonna put this in here, only for capacitors. A couple of you were asking me about the formula sheet. I want to make copies tomorrow. I want to provide you guys with the copies of the formula sheets, but by now you should be making your own as well, just in case, because we have several equations already, including what we did today on circuits. So those things you should have written down already, okay? Especially because we're changing topics tomorrow, going to current. Okay, so the energy will be 1/2. Everything has to be in SI units. So the capacitance, you write it like this, and V squared, you leave it at 70 volts. Like that, right? Yeah. 98. Not a lot. Not a lot, but still. All right. So it makes sense for electronics. That actually makes sense. And of course, remember you have combinations. So the more voltage, the more energy, the more charge. Right? Anyway, guys, so we conclude our topics of chapter 16 today with this last part of energy. As I said, please, if you have any questions, you have all the tools to complete assignments 2 and 3. So go for it. I will say now, of time, so you can work on a couple of problems after class, and then you have lunch or another class. You can get ready for it. And then tomorrow, before the lab, I'll be here to answer any questions, sort of like office hours. And then we have the lab, and we start with chapter 17 tomorrow, current and electric circuits with resistors, Ohm's law and all that. We should finish the topic on Thursday. That means on Monday, I will probably finish whatever we have left this week, and then answer any questions. It's going to be online, but I can answer any questions regarding exam number 1, which for sure will be on Tuesday in person. All right. By then, you should have finished assignment 5. So assignment 4 and 5, you should be able to finish them after Thursday, Wednesday's class. Again, I'll let you guys tomorrow how we're gonna do for exam 2, for quiz 2. It's most likely gonna be in person on Thursday, but I just have to double check the schedule. Any questions before we finish, guys, today? Double checking the attendance. Please check it. I only have, according to this, I have 4 students missing. So everybody else, I mark it already. So check it, please, before you leave. Yeah, okay, so that's easy. The students I have absent is Andrew, Sinan, Shruti, and Alexander. Only those 4 I mark absent. Everybody else is present. All right. And yeah, based on this, I think that's correct. All right, let's stop the recording.